So I like to describe some of the solutions people have come up with for the three middle problems that we discussed: the horizon problem, the flatness problem, and the relic problem. And the collection of ideas that are developed to address this go under the name of inflation. This was first publicly, in a well-known way, developed by Alan Guth in 1980, although there were Soviet efforts that we did not hear about until later. And Guth's idea is the following. Imagine that at early times, at 10 to the minus 36 seconds, below the gut energy scale, so after the grand unified theory time, but before the electroweak transition, the universe underwent exponential expansion by many orders of magnitude, 10 to the 30, say. Some large number, 10 to the 50. So an exponential expansion during which the scale factor grew by a factor of 10 to the 50. What does that mean? That means, remember, in exponential expansion, one's event horizon continually shrinks, and so our particle horizon, what we can see after that expansion, is a small fraction of what was then one particle horizon. The entire observable universe was some tiny little fraction of one region that was the pre-inflation horizon. So that solves the horizon problem. You give things 10 to the minus 36 seconds to equilibrate within the region of one horizon, and then you blow them up so they get pushed outside of their horizon, and then all the things that we are slowly seeing moving into our particle horizon, because our particle horizon grows, are actually things that we have seen before back in the first 10 to the minus 36 seconds. And so there is no news, there's no surprise that the cosmic microwave background is so uniform. It's so uniform precisely because we have inflated, and all the things that are out there are things that were causally connected with us prior to inflation. Similarly, the exponential inflation drives omega to 1. You can see that from the same equation that gave us the problem with fine-tuning before. Remember that h squared omega minus 1 is always equal to this. In this case, in exponential expansion, the Hubble constant is a constant, remember. And so what that means is that as a grows by a factor of 10 to the 50, say, this denominator gets bigger by a factor of 10 to the 100, and omega minus 1 has to shrink by a factor of 10 to the 100. So whatever omega you started with, by the end of inflation you have omega equals 1, and then you start the radiation-dominated era of our universe with omega equals 1 to very high precision, and therefore it's not surprising that we end up with omega equals 1 today. And similarly, whatever density of relics you think that the gut transition has produced is now decreased by spreading them out. And if you have expansion by scale factor growing by 10 to the 50, the relic density is diluted by 10 to the 150, and you don't have a problem with the fact that we have not discovered monopoles. So inflation is a great idea. And the question is, what does that mean? So we understand the kinematics. We understand how to describe exponentially expanding universes. We're used that to describe our future. But what does it mean? What is the dynamics? How do you turn a cosmological constant on and then off? Remember that we had sort of ideas in the context of quantum field theories for generating cosmological constants, and they were indeed huge. But how do you turn them on and off? Well, in these quantum field theories, in these guts, there are such things as sort of tunable vacuum energy densities associated to expectation values of fields, sort of parameters, dynamical degrees of freedom of these theories. The detail, a little bit beyond what we need. You can find, and Guth's idea was that the universe gets trapped in some false vacuum. This has large energy density, that triggers inflation, and this lasts for a short time before the universe sort of tunnels, decays out of this false vacuum to the true vacuum with lower energy. The energy difference is then released, that heats the universe, so the universe had been super cooled in some sense, and then gets reheated. The exit from the inflationary period into is into the current era, into the true vacuum, has all kinds of what is called graceful exit problems. So a model was proposed called new inflation or slow roll inflation, in which this tunneling event from a supercooled bubble nucleation type phase transition, like boiling water, is replaced by a very slow transition where the inflation area is a slow roll, where this parameter is, rather than tunneling suddenly, is very slowly evolving and then sinking into the true vacuum, and then subject to damped oscillations, which is how it reheats the universe. New inflation had its own issues. An improved version, or a modified version with other features and problems, called chaotic inflation, was proposed, where the phase transition is gone altogether and quantum fluctuations play the role of moving the field away from the actual vacuum whence it slowly rolls, and this occurs locally. And the idea is that one of these quantum fluctuations in some region of the universe creates larger energy density. This region then inflates very rapidly. The fluctuation is then very rapidly thrown outside the particle horizon and therefore can no longer decay. It's sort of frozen in, and then a new fluctuation occurs, and that too blows up and is ejected from the horizon. And so fluctuations are frozen in as they inflate. And this led to the idea that is the sort of topical one called eternal inflation. And eternal inflation, one really imagines that you have a universe with a large vacuum energy, so it's exponentially expanding and always has been. And it's infinite and it expands exponentially. Small regions of the universe can spontaneously decay to vacua with smaller vacuum energy. So these regions are still exponentially expanding, but exponentially slower than the ambient, if you want, universe. So these are these baby universe. They pop off. And from the point of view of the large universe, since they're not expanding fast enough, their intersection with the universe, with the universe they came from, is exponentially shrinking. And on the other hand, these regions are inflating, and so they undergo inflation and can then reheat and produce the entire history of our universe. And regions within them can further bubble off to even lower values of lambda, and so you get this sort of fleas on fleas picture of inflation, and the result is many disconnected, causally disconnected patches. This is the so-called multiverse. I have a feeling that I'm beginning to talk about fantasy. Is any of this real? Does any of this mean anything for us? And the idea, indeed, is that exponential inflation can freeze fluctuations. If you have some fluctuation, and then during the inflationary period, the wavelength of this grows beyond the particle horizon, it can no longer decay, just as it could not have formed at that size. And what that means is that these frozen fluctuations are the inhomogeneities around which dark matter and then subsequently baryonic matter can collect. So these are the seeds for structure formation. We've not had the time to discuss the theory of structure formation. It's also a little bit technical. But basically, these models make predictions about the kind of distribution of clusters and galaxies that you might expect. And so, in some sense, a model that predicts some kind of inflationary scenario will also make a prediction about the structure and the spectrum of perturbations, which will lead to a prediction about inhomogeneities in our actual universe, which you might actually compare with data. So, in an indirect way, these causally disconnected multiverse regions might actually is part of some larger model, something you could verify.